Hey everybody, Milk's here.
And MoNaCo too.
Yeah, Unit 10, Oxidation and Reduction, otherwise known as Redox. That's right, that's how we will say it for short all the time.
Page number 3. Trace. You got to know your key learning objectives to keep an eye out for what to know while we're doing our lecture videos. Or, heck, what to know if you got to go search it up again on yourself to do some private study.
There you go.
Here it is.
What we're going to learn this unit.
Define and identify oxidation reaction. So oxidation is a special type of chemical reaction. It has to do with electrons moving around between elements and compounds. So you've got to know how to find them.
Yes.
Recognize one.
And what it means.
Yes.
And vice versa with reduction reactions. Again, a very specific kind of reaction. You need to be able to know what its definition is, and you need to be able to know that you're looking at it when you see it. You need to be able to identify.
They are mutual and simultaneous. So
And opposite.
opposite. So it's like if you know one, you better know the other because it's the opposite.
It is the opposite. So don't get them confused though either.
Yes, true. We've got many tricks for you, but that's not the point of this video. You will need to know how to assign oxidation numbers to elements in a compound, in an ion, in a pure element, in a polyatomic ion.
Something we've done kind of in the past.
Back when we did ionic bonding.
Right, we had to crisscross.
To get the compound to have an overall neutral charge. So we're going to be bringing oxidation state back and looking at them ion charge-wise to see what is the element in this compound, what ion charge does it have right now.
Right.
A lot of that.
We're going to also identify the oxidizing and reducing agents. I'm doing this because this is MoNaCo's least favorite topic.
I hate it.
In this unit. The reason why is because these are opposite. So if I'm the oxidizing agent, I'm actually being reduced, but I'm responsible for the other dude being oxidized.
And if I'm the reducing agent, I'm actually being oxidized, but I'm responsible for the other guy to get reduced. It's actually like a triple backwards flip-flop, which is why I hate it.
Yeah.
I hate it.
But for whatever reason, the Regents
coming
loves
back.
it. So until we can get them to get rid of it, we're stuck with it.
This is follow my least favorite with my most favorite are the electrolytic and voltaic cells. This is the reason why your cell phone has a battery, why batteries work, period.
This is it.
Hearing aids, cell phones, anything that's got a battery, whether it's a fancy polymer ion battery or one of those zinc alkaline batteries in the television remote, works because of oxidation and reduction. So you're going to start to see diagrams of these cells and got to get to know to learn all the parts and how the electrons play and all that stuff.
Right. What basically happens is we take chemical energy and convert it into electrical energy.
Or we take electrical energy and force a chemical reaction to occur.
Right.
So that's why there's two different types of cells, voltaic and electrolytic.
And then, so next piece, of course, when you see these diagrams, just like the potential energy diagrams, you got to be able to label them all up. What's the name of the parts and what do they do?
Mm-hmm.
Okay?
Mm-hmm. And furthermore, in those diagrams, you have to be able to figure out which direction electrons are flowing.
Ooh, flow of electrons. That's electricity.
Yes, and so an oxidation or reduction reaction causes the flow of electrons, which is what runs your cell phones, your batteries, your powers. I mean, the headset that we're using to record this video is running on batteries right now.
Yes, it is.
And so a redox reaction is responsible for you even being able to hear us.
Here, I'm going to use the stored energy in my clicker here to click to the next one. Ready? Go.
There it goes. And bringing it all back around to
Table J. We are going to really dig into Table J now because this is going to help us understand, are these reactions what we call spontaneous or not?
Right.
And spontaneous in chemistry is a little bit different for us. That means, does it go all by itself, or do I got to give it help?
a little push.
Yeah, if I don't got to give it a little push, that's spontaneous.
All the batteries that are powering our devices right now are running on spontaneous reactions because they produce a voltage whether you're using it or not.
Right, all we got to do is complete the circuit.
Right, and then all of a sudden my cell phone powers up. Vice versa, your cell phone battery gets dead. You got to plug it into the wall and zap it with electricity to force it to go backwards to recharge itself.
Right.
Not spontaneous. I mean, batteries don't charge themselves by themselves. You got to plug them in.
Right. Isn't that
So
funny how that works?
So, So that's it. Keep an eye out for these topics. If you don't understand them after you see the lecture on them, search up the topic on yourself.
Yeah, come see us.
Yeah.
Seriously.
Thanks.
Questions is always good.